lecture. This was lecture 13, so this will be 14. Why is lecture 13 not showing up? Anyway, let's forget that. So, lecture 14 then. So let me just go ahead and put this up. I'm just opening my chat box, that's all. So question for you guys, how many of you are reading the book? The reason I'm asking is, once we have transitioned, do the notes seem to be enough? I'm not talking about your go-to places like Khan Academy. You should have that, and I'm thinking you have that. Whatever it is, Paul's on online, Khan Academy, whatever the other sites you used to. But okay, so do the notes fill up a big gap, or you're still 50-50 with the other things that you're using and the notes?
I typically just go off the notes.
So you are not going to the other sites too much then?
Oh, no, I mean, I go to some sites, I just don't typically read the textbook because they just...
Okay.
It's a bunch of letters and mumbo-jumbo.
In some ways, I'm thinking of the future. In some ways, I'm thinking of the fall, that do I have to, are the notes enough, or do I have to have some videos attached or something? For you guys, I did not do it because I did not want to burden you with, I know everybody is making you watch videos. I'm talking this off of my daughter. She's so tired of watching video after video after video. Oh, there you go, Cecily. Yeah, the web assign. So the web assign and the notes seem to cover most of it. So Bhavneet watches YouTube videos, okay. So I don't need to bombard you with any other videos, right? Good. So I think I'm going to leave it that, and let's start. So here we go. We are talking about series. And I am the queen of repeating, so I'm going to repeat again. So what is series? Oh, it's an infinite sum, which is n equals 1 to infinity an, which is a1 plus a2 plus a3. So I'm going to say, when you say series in my very simple language, I'm going to say, oh, you are adding, so it is addition of terms. Well, how many are you adding? Infinitely many. What kind of terms are you adding? There's no rule, any kind of terms. So I'm going to say, oh, there is a sequence, there's a list, there are these terms. So I'm taking these terms and I'm adding them. What do we want to know? Here we go. The question we want to know is this infinite sum finite? If the answer is yes, then I say the series converges. And of course, I want to find the sum. If the answer is no, then I know the series diverges. Which means it is plus or minus infinity or does not exist, which means limit of Sn as n approaches infinity is infinity plus or minus infinity or does not exist. So what am I interested in? The convergence series. So I'm just going to remind you that is there a series like that adds up to a finite sum? And the answer is yes. And very simply, if you make up a geometric series, and I'm just going to make up n equals 1 to infinity, say 1/3 to the n. So I'm adding what? And I can even go 0 to infinity, and I wanted to introduce that. So here we go. So this is 1/3 to the 0, 3, 1, 3 squared. Take this, people. So first term, and this is just a warm-up, so let's do it quickly. So first term is?
1.
Very good. Common ratio?
1/3.
Very good. Remember, it's this over this and this over this and this over this. And so it's 1/3. So what do? I look at the common ratio. Less than 1. I know it converges. When you say converges, that means what? Oh, this series adds up to a finite number. That's just what you're saying. And I want to know that finite number. So if I want to know that finite number, because it's a geometric series, I know it adds up to a over 1 minus r, which is 1 over 1 minus 1/3, which is, 1 over 2/3. Where are we going wrong with this? We're okay, right? Yeah, we're okay. So this is 2/3. So 1 over 2/3 would be what? 3/2? Right. Does this add up to something finite? Yes. So infinite sum does add up to something finite. We want to do something else with it. And what is it? And here, I'm going to throw something in. So just to take that concept a little bit here. So here's another series for you. So tell me, how will this series go? So this will be what? X to the 0. And so what does that mean? So tell me, is this a geometric series?
Yes.
Very good. And the first term is what? Just x to the 0, which is 1. The common ratio is what?
X.
Very good, sir. And then what do we know about geometric series? See, I don't know this x. This is a variable. You're giving me x, which you're not telling me what the value is. But what do I know? I know if the absolute value of x is less than 1, then the series converges. So what do I mean by absolute values of series? X is less than 1. Oh, -1 is less than x is less than 1. I know the series converges. Well, if you know that, then it converges to what? As Trent typed, if it's a geometric series, it converges to a over 1 minus r. So what is a over 1 minus r here? 1 over 1 minus x. So instead of a number now, you have this sum adding to a function. That is where we are headed. So this, I know, is a function. I can graph this one for you. But more importantly, when is this true? Is it true for all values of x? No, it is only true for these values of x. So in some sense, these two entities are equal if x is between -1 and 1. And that is a fascinating thing, that an infinite sum now adds up to a function. Oh, if it adds up to a function, then I know I can integrate this function. I can differentiate this function. That is where we are headed. But before we go there, I'm going to show you some very nice things today. So before we go there, we want to separate the series which converges from the series which diverges. Because if the series diverges, Ni, which is not interested. If the series converges, I want to know what it adds up to. I want to know the sum of this series. And so let's start. So how to do this? And that is why we have those kind of tests. So number 1, I'm going to find Sn. Sn is sum of first n terms. I'm going to take limit. As Sn approaches, if it is a finite number S, then I know that the series converges. So S is a finite number. And if it is infinity or does not exist, the series diverges. Not only that, if you go this route, then the sum of the series is that little s, is that limit. So the limit is indeed the sum of the series, which I'm going to say completely opposite of this today, later on. But right now, this is it. So So here we go. And I want complete attention now because, this is not in any book or any YouTube video or anything like that. So do I have your complete attention? And I'm going to take 2 minutes. This is a story that you probably don't need to hear, but you should hear it. And I will tell you how it pertains to the material. So, not interested, Cicely? Okay. So here's the story. So when I was little, I know you don't want to know these things, but, hopefully this will make it fun. So when I was little, I was very fond of something called Eclairs chocolate, and I used to eat a lot. That was a great part of my diet at one time. My dad just asked me not to eat them because he said, and he's tried all sorts of reasons, and when that didn't work, he said, and there used to be a lady that used to live downstairs, and she had those brown kind of teeth. She was very pretty, but you wish that she wouldn't smile because then everything would just go to dust, literally, because her teeth were like that, and that her teeth were like that because she was chewing tobacco. It had nothing to do with eclairs. So my dad tells me that, if you continue on this path, then you're going to have teeth like that lady. And I was really scared and I wouldn't eat the chocolate. Now, you have to understand, this is a 5-story building. We used to live on the 5th floor. She used to live on the 4th. And there were no elevators at that point, so you had to walk up the stairs. So one day, me and Dad are walking up, and she comes out, and she's walking behind us, and then she stops us, and she offers me, guess what? Eclairs. I denied it. That went on for a while. She said, take it. And I said, no. She said, take it. I said, no. And then she looked at my dad. I said, what's wrong with your child? Why is she not taking eclairs? My dad look at him, he nods to me, and he makes a gesture that take it. And I'm like, I'm totally surprised. I said, when I wanted to eat this, you scared me. You told me that little thing, and a little nugget that I would have teeth like her. So she asks me, why are you not taking it? And guess what? I told her the truth. So I told her, my dad told me I would have teeth like hers if I did that. After that, I ran upstairs. My daddy comes, a very exhausted man. 20 minutes after, I'm thinking he was just apologizing to her and apologizing and explaining, I don't know what he did. But he said, it's not worth telling you anything because you have no idea of what to hide and what not to hide. So how does it pertain, people? And here it goes. Hope you enjoyed the story. But how does it pertain? So what happens? You cannot find SN each time. It's very hard to find SN. That means what? This was a good way of doing it, but she smiled. So every time she smiles, you have to do something else, which is what? Here we go. Number 2, you will check if it's a geometric series. But geometric series only converges when absolute value of r is less than 1. If absolute value of r is greater than or equal to 1, then it diverges. But not all series are geometric, so she smiles. If it were, then we would be done. So here we go. She smiled. So we need something else. So we said, number 3, oh, it could be a telescoping series. But when I write telescoping series, it is really, really going back to number 1. But then not all series are telescoping. So it's not easy to write. So not all series. So she smiled. So, number 4, you said, oh, I can do the test of divergence. So what is the test of divergence? Take limit as n approaches infinity of an. But this limit has to be non-zero or does not exist. If that happens, the series diverges because you're testing for divergence. So never, ever say it converges. But what if limit is equal to 0? Well, she smiled. And that nice test has gone away. So number 5, we came to something called the integral test. And today I'm going to do a fallacy of that. I'm glad that you enjoyed that story, but this is how I go about it. This is what I tell you, that she smiled. So, integral test, what should happen? First, you start with a series. You've done the checklist, which means what? You've checked it was geometric, you've checked if it was telescoping, nothing has worked. And I can make a series for you right now where nothing would work, but I want to do 2 things as one. So I'm just going to write this. So what is it that we do? Oh, we come up with a function. So what is it about this integral test? And I think I'm going to go back and, there was some that undo button. Where did that go? So here we go. So what is this integral test? Oh, the integral test links your series with improper integrals. And to make this link, because this link does not work all the time, which means what? She smiles again. So what do we have to do? Come up with f, which is the corresponding function, such that what? F at n is an. How should this f be? Oh, it should be continuous, positive, and decreasing. So I will show you why these 3 conditions, especially the last one. So continuous and positive are okay, I can talk about. So how do I show that f is decreasing? Remember, when you are saying f is decreasing, you are claiming that f decreases always over the interval, which means for this, you will have to use derivatives. And then what should happen? Then you take the corresponding integral. So then you take integral 1 to infinity f of x dx. If the integral converges, series converges. If the integral diverges, series diverges. Well, we always said if it converges, I want to know the sum of the infinite sum. I want to know what it adds up to. So I'm going to caution you, no, here, the limit of the integral, I'm going to write this. So no, the value of the integral, and I'm going to prove every single point I did there, value of your improper integral, which is I, is not the sum of the series. And I'm going to give you an example of that one. I'm just going to say, and I'm going to pause. I know you're writing with me. So if f does not satisfy one of these, then guess what? She smiled. So you want something else. So talk to me, people. So far, so good. Are you writing? Should I pause? Or be okay? So I told that bit of a story, and I kind of took your time because I want you to know why so many tests. Why so many tests? Because she smiled. That is why. Because every test you come up with has bad teeth. And it's a beautiful test. So, Cicely, thanks for responding. Let me know when I should continue. But this is where we've come. How many tests are remaining? 4 of them. So we have 9 tests just to separate a series that converges or diverges.
Lovely. Do we need to memorize all of them?
But Russell, don't you think they're incredibly interesting? I mean, it's just interesting that you were, Karan, I did not get the, oh, you mean the smile idea? The 4 tests? Okay, I can't get that. But Russell, for you, I'm just going to say, because you're talking to me, the infinite series adds up to a function, Russell. Who would have thought that? And we are going to use that extensively. Oh, okay. Now I get it. Okay, thank you, Cecily. No, there's just one more test, Karan. And I'm doing this still like on Canvas like last time because I want to give you partial credit, what we are used to, and then you go take the final, which, probably, but wait for me. I don't want to talk about the final again. So here we go. So here are the examples now. So we did one example last time, and I'm going to run it. And I hope everybody is caught up. So where is Nera? Nera, are we ready to go? She's a good bellwether, because I know she writes and she takes beautiful notes. So are we okay, Nera?
Oh, I'm good. Thank you.
Okay. So here we go. Here's the first example. And this we did last time. This is called a harmonic series, which, we ran to. And the harmonic series really comes from music. So it's a whole note, a half note, a third note, a quarter of a note, and so on and so forth. So this is called the harmonic series. So first, you're going to write it out. Right, we did. Last time, then we said we came up with a function, fx is 1 over x. We made the connection, which is f at n is 1 over n. So in other words, when n equals 1, f at 1 is 1, which is the first term. N equals 2, f at 2 is half, which is a2. And that's the connection I'm talking about. N equals 3, f at 3 is 1/3, which is a3, and so on and so forth. So that takes care of that corresponding function. So this is the first step you have to do. Then we are saying, because we made that connection, that x is going to be replaced by n, and I know n is going from 1 to infinity. I'm ready to say, because n is greater than or equal to 1, or x is greater than or equal to 1. And remember, we are talking about the function now. So we're looking at the function. Because x is greater than or equal to 1, I know f of x equals 1 over x is continuous and positive. Because we know it has a discontinuity at 0. And we are not even talking about 0. We are talking about x, values of x to be greater than or equal to 1. So that's easy to do. F prime x is negative 1 over x squared. So f is always positive. And again, you're going to mention here x is greater than or equal to 1. Well, you don't have to, because this thing is always going to be positive, even if you put a negative number in. So you're going to say that, okay, so f prime x is always going to be negative. So f is decreasing. And the last part, we did the corresponding integral, which is 1 to infinity 1 over x dx. And we said, I know this diverges, because from the improper integrals, I know it diverges for values of p less than or equal to 1. So it was kind of that p integral, if you want to call it. And I'm going to end it there. And here we go. I'm just going to say, if I applied the test of divergence to this one, then the limit as n approaches infinity, 1 over n is what? Remember, the test of divergence is you just close this and you take the limit of this one. And this is 0. So I'm just going to write that limit as n approaches infinity, 1 over n is 0, but summation 1 over n equals 1 to infinity, diverges. And I want that there. Now I want all of you to do my example 2. And at this point, you can unmute yourself, but you're going to answer this one. So consider this series. Write down the terms So they are going to be 1 plus 1 over 2 squared plus 1 over 3 squared, 1 over 4 squared, right, people? If you want me to pause, let me know. I will pause, but I want all of us to work this together. So are we ready? So you can type a yes in there, you can unmute yourself and you can say these things.
Yep,
Okay.
I'm ready.
So almost that says Trent, so I'm just going to give him a minute. He is my reader after all. So Trent, let us know. Okay. So here we go. So let's get first things first out. That this is not a geometric series, right? So let's go through that checklist. So it's not telescoping because I cannot use that partial fractions. I don't know how to add 1 plus 4th plus 9th plus 16th all the way to 1 over n squared. I don't know the formula for this one. So it's not geometric. So that's gone. What about the test of divergence? Well, if I do T of D, then limit as n approaches infinity, 1 over n squared is 0, just like here, which means she smiles. Meaning test of divergence at this point is the beautiful test just goes away. It's not doing anything for us. So we're going to come to our next option, which is integral. So tell me, what function are we talking about here?
One over n squared.
Very good. So I'm going to say, Aaron, go when you mention the function, it's 1 over x squared. You're absolutely right. We are going to make the connection that f as n is 1 over n squared. So that is you connecting the function to your series. And you are going to justify that, okay, if I put n equals 1, then I get a1. If I put n equals 2, I get a2. This is just a check for you. If I get n equals 3, I get a3, and so on and so forth. So it's the same thing. So we start with this one then, because we're talking about the function now, and then we're going to link the function with the series. So tell me, 1 over x squared, is it positive and continuous? So I'm going to say it's positive and continuous. Why? Because x is greater than or equal to 1, isn't it? Because you've made the connection. So tell me, what is f prime x now?
So,
Go on.
quick question.
Sure.
Do you have to specify that x is greater than or equal to 1?
Yes, because, you know, in this case, I would say you are okay, because I see what you're getting at. There's x squared here. So maybe not, but it's a good idea to carry this with you, because you will see how it is relevant now for the derivative, which it was not earlier. Does that answer your question?
Yeah, I think so.
Okay. So if we take the derivative of this one, what is the derivative of this? What is the derivative of this? Very good. So I'm going to say to you, Aaron, keep with the x because you're talking about the function. So it's negative 2 over x cubed, which is going to be what? And at this point, you do want to mention x is greater than or equal to 1, Russell, because if you don't, if you put a negative, this is going to be negative. So at this point, I would still mention, oh, x is greater than or equal to 1. So this is always negative. So f is decreasing. So I look at that integral, which is 1 to infinity, negative 2 over x cubed dx, which negative 2 is a constant. So I can write this as negative 2 integral 1 to infinity 1 over x cubed dx. So tell me, does this converge or diverge? Because I don't want to confuse it. I'm going to use that improper integral. We know that result. So Cecily, we are looking at the results because come up here for integral test, you want continuous, positive, and decreasing. No, to use the integral test, F has got these conditions that it is continuous, positive, and decreasing. If F does not have one of these false paths, she's mine, meaning integral test doesn't work, Cecily.
Right, but you look, if you scroll down, you use the derivative as the integral instead of 1 over x squared.
Oh, that's what you're talking about.
That's what I was talking about, yeah.
Oh, yes. I did. My bad. So 1 over x squared. You are absolutely right, miss. I didn't even realize that. Because, my mind is on other things. So what about this integral now? Converges or diverges? Thank you, Cecily. So this one converges or diverges? Very good. Why, Karan? Because we know p equals 2 is greater than 1, so it converges. Well, what about the sum? Integral test, no. And I'm going to prove to you that the value of this integral does not. And that's why we don't even bother computing the limit of the integral. So we are going to say this converges. What happened? So now you're saying n equals 1 to infinity, 1 over n squared converges. By what? And this is what I want you to write. So after you do that, remember, when you're saying this one, you are saying the integral converges. So how do you go from integral converges to the series converges? And that bridge is by integral test. So yes, I want you to mention the test used every single time. So you are going to go that by integral test, you are making this connection. So it is by integral test that this series converges. Right, Joshua, so you got that. That is what the improper integral. So go back and you have that improper integral that we did. So now I'm going to say, look what happened. Limit as n approaches infinity, 1 over n squared equals 0. But summation 1 over n squared, n equals 1 to infinity, converges. I'm going to put it in a box. I'm going to look at the two together, and hopefully we can do that. So here it is. And if you see the first part of the page, then what did we say? This one, what is this? This is a test of divergence. So if you do the test of divergence, you got limit 0 here, but the series actually diverges. If you use the test of divergence, you got the same limit 0 here, but this time the series converges. And that is why the test of divergence fails when limit equals 0. So you ever get confused by this one, I want you to remember two series. 1 over n, which diverges, which is the harmonic series, and 1 over n squared, which converges. And both of them have limit equals 0. And that is why test of divergence fails. And Joshua, I'm going to take that cue because you asked that question. So here we go. So what does improper integral do? And then I'm going to pause and take questions if you have any. So here is my last comment. So what does the improper integral do? Just that you had this improper integral, which you said converges, and we proved this for p greater than 1 and diverges for p less than or equal to 1, we can have the corresponding p series, which is summation n equals 1 to infinity, 1 over n to the p, which will converge when p is greater than 1, and it diverges when p is less than or equal to 1. How do we make this connection? Integral test. So it is by integral test that you can connect an improper integral, I stands for improper integral, with an infinite series. with an infinite sum. I'm going to pause. Questions? So I'm going to take one from your book as an example of integral test. And let's see if we can go ahead and do this one. I'm just trying to look for an example, or I'm going to just take the one I like. There was one I really liked. Where did that go? So no questions there? Are we all right? And so there's one particular that I really, really like. I think I'm going to do that one, but one from the book before that.
I think Cecily had a question.
Okay. Go on.
It's in the chat.
So if we use p-series, can we write that instead of writing by the integral test? Yes. So you can use p-series instead of that, but you have to know connection. You have to know where it comes from. Yes. So you can quote this as a p-series, and you can say that I know how this series behaves. Yes. So Joshua, I'm hoping it cleared up the questions you asked earlier, and Karan seems to have answered it, but yeah. So finally I found the one I like. Here we go. So here is the example from your book, which is 1 over n squared plus 4. I like this one because it checks off all the boxes for me. So here is the example. So let's write it out. First thing, I want you to write out the series, which is 1 over 1 squared plus 4. I don't know about you, but I'm systematic. I kind of write it like that because that tells me this is n equals 2. 1 over 3 squared plus 4, which is n equals 3, and so on and so forth. So I just get a feeling for the series, which is what? 1/5. And this is going to be 1/8. And this is going to be 1 over 13, and so on and so forth. Great. So do this quickly for me. Geometric? No, right? Because this over this is not the same. So the easiest thing that we wanted to do, geometric, is not. What about the test of divergence? What do I mean by test of divergence? You're going to cross this, and you're just going to take the limit of this as n approaches infinity. So tell me, what is the limit of this as n approaches infinity?
0.
It would be 0. So test of divergence fails here. So you can't use that one. Is this telescoping? And the answer would be no, because for telescoping, what needs to happen? Partial fractions, yeah? And when does partial fraction happen? When your denominator q can be factored. So you are saying this cannot be factored. No factors there. So no, it's not telescoping. So you have exhausted everything that has come before it, which means you have to go to integral, which means you have to come up with a function. So f of x would be, so say it or write it, people.
1 over x squared plus 4.
There we go. So I'm going to just make that connection that f at n is 1 over n squared plus 4. Why do I write this? Because I just want to let you know, look, x has taken the place of n. That's all. So when I talk about x, I'm really, really talking about n. Now, Aaron, this one is for you. Now, we don't talk about this. We start talking about function, because that is what integral test says. Now, you don't talk about the series. You don't talk about this one. You start talking about this function. So, tell me, this is positive and continuous? Why? I think the easiest thing to say would be x is greater than or equal to 1. The more in-depth thing to say would be, oh, this is positive everywhere, because x squared plus 4 would be 0 for what values of x? For imaginary values of x. So 1 over x squared plus 4 is really continuous and positive everywhere. But I'm just going to say positive or continuous because x is greater than or equal to 1. So next thing we have to check is the derivative. So f prime x, what would the derivative be? And for the derivative, I'm just going to say, I'm going to think of this as x squared plus 4 to the negative 1. That is the quick way for me to take a derivative. So the derivative would be negative 1, negative 2 times 2x. So f prime x is negative 2x over x squared plus 4 squared. Very good. And so, why is this always negative? Because that is what you want to justify. And I'm going to say this is always negative because look, this x is always greater than or equal to 1. So the numerator is always going to be negative. This one we already know we have a square there, so this is always positive. And I'm going to pause a little bit. Are we okay then?
Yep.
So f is decreasing. And so we are going to look at the integral now because it has passed, your f has passed all the tests. So now you can apply the integral test. So I want to say here, when you do this, it is like this green signal. And I'm just going to have that green signal. So here is the green, meant to get the green. So here is that green signal to do what? To apply the integral test. Meaning I'm going to look at this integral 1 to infinity 1 over x squared plus 4 dx. So this is your improper integral, which means what? This is limit as b approaches infinity 1 to b 1 over x squared plus 4 dx. And what is this integral? Remember that one? Or you are going to do your trig sub, whichever way, but tell me what this integral is. So you can unmute yourself, take your time. Here we go. So I want to do limit b approaches infinity. What is this integral from 1 to b? Very good. So it is indeed half tan inverse x over 2. And so you're going to have half tan inverse b over 2 minus half tan inverse of half, whatever that is. So we want to know what happens to this guy as b approaches infinity. So what happens to this one as b approaches infinity? Again, take your time, let me know. Very good. So this is half times pi over 2 minus half tan inverse of half, whatever that may be. But can we say this is pi over 4 then? Because remember, this is the limiting value. So this is pi over 4 minus half tan inverse half, which is what? A finite number when you put it in your calculator. So the integral converges. If you want, you can say the improper integral converges. I converges. So now you're going to say, so by integral test, series n equals 1 to infinity 1 over n squared plus 4 converges. But I do want to say it again. When it converges, do you know what it adds up to? Do you know the sum? The answer is no. We are going to estimate the sum, but we do not know the sum. So what am I trying to say here? No, this is not the sum of the series. This limit, so limit of the improper integral, is not the sum of the series. And why is it not? I'm going to prove to you with an example why you can't say the two things. And this is my favorite example. I love this series. It's very simple and it does the job. So no questions there? I'm going to pause if we have any questions. Remember, integral test. Go with the name. It integrals to, yes, current. It only tells you whether it converges or diverges, but it does not find the value. Exactly what you wrote there. I'm going to answer that question. Why doesn't it find the value? Why is not the limit of the integral the sum of the series? Because after all, when you did that Sn, it was, wasn't it? But no, this time, the limit of the integral is not sum of the series. Because in some ways you can say that you are looking at another entity, which means what? You are just adding some terms of the series and you're looking at, and Cecily will get this because I think she's done discrete, if I remember correctly. So it is, you are having a discrete entity, which is series, and you are looking at a continuous entity, which is functions. An integral test connects the two. In what case? In only these three cases, when it is continuous, positive, and decreasing. If one of these falls apart, you can't make the connection. And because you're looking at two different entities, having a sum of one entity, you can't relate it to the limiting value of the other. That's the conceptual part of it, but I'm going to do this with an example. So ready for the next one? So I just wanted to pause if there are any questions you have about anything with this example, because today your homework is going to be full of those integral tests. So we move on then. Here is, I want sort of all of you to chip in if you can and answer this one. So consider this series. I'm going to write up here. So this series is for what? Exactly that the limit of improper integral is not equal to the sum of, or it's not equal to infinite sum. I'm just going to say that. And we know infinite sum is the series. And for that, I want you to consider this series. So this is going to be so write it out for me. So this is going to be e to the negative 0 plus e to the negative 1 plus e to the negative 2, so on and so forth. So I want you to look at this series in two ways. And for that, I'm going to come back here and divide it into two. So if I write this out, then e to the negative 0 is 1. This is 1 over e plus 1 over e squared. Tell me how you see this series. So this is what the series looks like. So go on. Very good. So current started us off. So I want you to look at it as a geometric series. So what? A equals 1. The common ratio is 1 over e. Is 1 over e less than 1?
Yes.
Very good. And so the series, we know it converges. Oh, it's a geometric series, so I also can find the sum. I know the sum is a over 1 minus r. So it is 1 over 1 minus 1 over e, which is going to be e over e minus 1. So I know this is the sum of the series. So I know that this series, n equals, so I'm going to erase this. So I know that this series, which is summation n equals 0 to infinity e to the negative 1 n, actually adds to this. This is the actual sum. So far, so good, people. Now, just to prove my point, I want you to look at this in terms of apply the integral test. So give me the corresponding function. So f of x should be, very good, e to the negative x. So tell me, e to the negative x, is it positive and continuous? And for that, I'm going to say I have a graphing calculator. I just graphed it. It looks, e to the negative x looks something like that, isn't it? It's an exponential function. So of course, it's positive and continuous. So we don't even have to mention the interval at this point because it's continuous positive on its entire domain. So that took care of that. So what about f prime x then? So f prime x is going to be, and what is it going? Very good, current e to the negative x. And so this is always negative, isn't it? Because this is positive. So this is always negative. And then at this point, you should say, why am I doing the derivative test here? I have graphed the function. I know f is decreasing. Well, if you actually graph that on the test for me, I'm going to accept it. But yeah, you saw that f of x is continuous, it's decreasing. And then I know I'm doing not really doing it in order, but I should write it here that, oh, f at n is e to the negative n. And this time, n is greater than or equal to 0 and not 1. And we are okay because the nature of the function itself. So now we start talking about the function. We take the integral 0 to infinity of e to the negative x dx. So this is going to be 0 to b, limit as b approaches infinity, e to the negative x dx. And the integral is going to be what? Negative e to the negative x dx. Sorry, not dx, from 0 to infinity. And then we're going to take the limit as b approaches infinity. So this will be what? Negative e to the negative b minus negative e to the 0. So I claim this is 1 minus 1 over e to the b. Did I do that right? So just look at this one.
Yeah.
Just do the algebra, and that's all I'm doing. So now I want to take the limit as b approaches infinity. So what is the limit of this one as b approaches infinity?
Well, I believe it'd be 1 because 1 over e to the b goes to 0.
Very good. So this goes to 0. And so what are you saying? Oh, you are saying this integral converges. So by integral test, the series converges. But look what the value of this integral was. The value of the integral, so value of the improper integral is 1. And the sum of the series, I know, is e over e minus 1 because I have independently done that. And so the value of the improper integral is not the sum of the series. And this is what I proved to you. The limit of improper integral, the limiting value. When I say value, it's the limiting value. It is not the sum of the series. Are we okay now? Each and every one of you.
Yes.
Very good. So I don't see any questions, so I'm going to pause there. No, Karan, we don't find the sum in that case. We estimate the sum, and I'm going to do estimations later. So answering Karan's things, so here we go. Let me write that comment right now and finish integral test. So if I get to apply the integral test, I do understand, I'm repeating myself, the value of the integral is not the sum of the series. So the question is, how do I find the sum? Well, the best thing you can do at this point is estimate the sum. And for me, I like to do estimations after. So at this point, I'm sticking to what I said. It's just separating the convergent series from the divergent series. Again, one of my bad analogies, Karan. It's right now you are just saying a series steps out. That's the bachelor car rolls in. The girl steps out. Right now, you're just going to decide whether to give the rose or not to give the rose. So just separate them from possibilities to not interested. Does that make sense? We're going to get to know the girl a little bit better afterwards, exactly like that series. Do you have any idea what I talk about?
Yeah, like 50% of the time.
Okay. I will take 50%. We are online. So if you are understanding me 50%, I'm going to declare that, and this is just my declaration, is success. It's how I define success. How about the others? Either you're playing Red Dead Redemption or you are in deep thought. So, okay. Okay. So, I have too much fun with you guys. I really do. And I hope you do too, and it doesn't just get dry and boring. So the story continues, people. Remember, today it is She Smiled Day. So you really do. Oh, you're reciting the verse, the whatever. Yeah. So here we go. So here's a new series for you. So here's my example. And I'm going to put two series in front of you. Oh, I have to be careful about this one.
So it doesn't matter where a series starts?
No, it doesn't. Because all you're saying is, I'm saying here the first term is, it is still the first term. It just corresponds to n equals 2. And here, this is still the first term. That's just the first term corresponds to n equals 1. Remember, it's a great question, Russell. I'm just going to say both of these are infinite sums. Right? You're still adding infinite number of elements. It doesn't matter where you start, because you're not stopping anyways. Does that make sense?
Yep.
Let's start writing the first one. So I'm going to call this number 1 series. I'm going to call this number 2. And I told you today was the day where I'm going to introduce you to this one. So if I write number 1, then the terms come out to be 1 over 2 to the 1 plus 3 plus 1 over 2 squared plus 3 plus 1 over 2 to the cube plus 3, and so on and so forth. So I'm going to write that number 1 turns out to be 1 over 5 plus 1 over 7 plus 1 over 11, and so on and so forth. So 1 over 2 to the 4 would be what? 16, so that would be 19. So let me just make a comment. Oh, all of them are positive, so maybe not. So here is your second series, which is going to be 1 over 2 to the 2 minus 3 plus 1 over 2 to the 3 minus 3 plus 1 over 2 to the 4 minus 3, and so on and so forth. So this is 1 over 1 plus 1 over 5 plus 1 over, so this is what? 16 minus 3, which is 13, and so on and so forth. So let's go back and let's talk about this one. Which is this number 1. So I want to quickly write here. Geometric? No. Telescoping? No. Why? Because the denominator can't be factored, so telescoping is a no. What about the test of divergence? Meaning I want the limit of this thing as n approaches infinity. That's the test of divergence. So what is the limit?
It's 0.
Very good. So the limit is 0. So test of divergence fails. You can't use that. That means you are back to the integral test. Well, if I do the integral test, then what is the corresponding function for this one?
1 over 2 to the x plus 3.
Very good. And x is, and I'm going to write that f at n is 1 over 2 to the n plus 3. So I think positive, continuous, all are taken care of, which is fine. But I'm supposed to integrate this. The question is, do you know how to integrate this function? Because integral test depends on what? That you should be able to integrate that function. And can you integrate that function? And at this point, I'm going to say no. Yes, Aaron, this time you're out of right. In other words, it's incredibly hard to, you can't integrate that function. I do not know. I've done many techniques, but no. So I'm going to go back. Remember, she smiles. So I'm going to do she smile for integral test. So there are 2 points, not 2 instances where she smiles at. One is here. So if one of these falls apart, you can't use it. The other thing is, I am talking about when the integral converges, series converges, meaning I should be able to integrate that function. So if I can't integrate f, she smiled. Meaning what? If you don't like that she smiled stuff, take it out. It's not for you. Just say the test fails. That is what I'm trying to get at. So you don't have to say she smiles, but that's just was my take on it, sort of a fun take on it. But if it annoys you, you just can say, oh, the test fails. Because, this test hinges on what? It hinges on that I should be able to find the integral in the first place. If I can't find the integral, then no. Then this test, I can't use it. So we need another one, don't we? And here we go. So I'm just trying to look. This was number 5, I believe. There we go. So we need number 6. So I'm just going to write some comments here. So what happened to that integral test? I didn't even bother to check the functions, but I cannot integrate. So for the integral test, I should be able to integrate. Integrate what? Should be able to integrate 1 to infinity f of x dx. And it seems like I can't here. So no, I cannot integrate. So all the tests I know so far seem to have failed me. That means we need number 6. These are 2 tests. We're going to do them together. They are the comparison test and the limit comparison test. So So what about this comparison test? Oh, you'll be fascinated to see the connections. So the idea is, and I'm going to write the idea behind that. I will compare two series. So in other words, I'm going to compare summation AN and summation BN. And so this is the problem, because this is what I wanted to know, the series is convergent or divergent. So what is this BN? I have to come up with it. And now all of you stop writing and just pay attention. So let me say that for n greater than or equal to 1, AN is always less than or equal to BN. That means what? A1 is less than B1, A2 is less than B2, A3 is less than or equal to B3, and so on and so forth. So it seems your series, if I add up your series, this infinite sum, whatever it is always going to be less than this infinite sum. Why? Just because every time this guy is more or equal. So tell me this. If somehow you know that this converges. Hey, so can I say this is the big guy? So if this converges, meaning what? It adds up to a finite number. What can you say about this one?
Doesn't it also converge?
Very good. So it converges. That is it. That's the comparison test, really. And now I'm going to say it. Very good. Yes, Cecily. And now let me put it, if AN is greater than or equal to BN, and if this one diverges, somehow I know this. So isn't this the little guy? So if these sums, the little sums, if they diverge, what happens to this one?
It diverges.
Very good. And I'm going to write it here, but what if this diverges? What if the big guy diverges? Then what can you say about the little guy? Nothing. I'm going to say inconclusive. What if sigma Bn converges? What can I say about the big guy? Nothing. Inconclusive. Because as Cecily pointed out, yes, this looks like the comparison test or theorem for I, isn't it? The improper integral. It's exactly that. Because remember, again, the connection. Improper integrals are connected to your infinite sum. But then here is the idea. So the ones I wrote in red, she smiled, isn't it? That means what? To make this work, what are the two things I need? I need the right relation. So number one, I need AN less than or equal to BN, and I need sigma BN to converge. Then I can say sigma AN converges. Number two, I need this relation, and I need sigma Bn to diverge. And then I can say sigma An diverges. More importantly, I'm going to tell you why a little bit later, this only works. So this test, both of them, only works for series of positive terms. But this shouldn't surprise you, because what did you say for integral test again? F of x has to be positive, continuous, decreasing. So weren't you talking about positive terms here as well? And the answer there is yes. So you need comparison and limit comparison. comparison test. So I think I'm going to stop here. We are at the end of the class. So you need these two. So what's going to happen in next class? Next class, I want to prove. So let me first write about the test. So this, your comparison and limit comparison, are sections 11.4, which I'm going to finish next time. So today you're going to deal with the integral tests. The homework today is for integral test. Then I'm going to have this one next time. And on the test, you are going to deal with chapter 8 and 11.1 to 11.4, which is convergence of the series. And yes, this is open book, open notes. So I would say, or I would suggest that make a cheat sheet for yourself. Write all these things that I'm writing here on one paper. This is just to optimize this 1, 2, 3, 4, 5 that I keep writing. Add 6 to it. All of this should be with you. I will put up a document which you can use, which lists all these tests and the tests that are coming after as well. So, but I strongly recommend that write all of these tests on a sheet of paper. All these tests, use it, and use it right now as you're doing homework. Even though you know that today's homework deals with integrals, I want you to look at the series and still go through that thought process. So I still want you to say, oh, this is not telescoping, this is not this. So write all these tests and use that, and start using that right now from today for the homework. That's due on Friday. So these are my office hours. I know you have classes to go to, so I'm going to stop.